All right, let's take a look at similarity within polygons. Now, this is a bit of a new concept, right? We've talked about congruent polygons before. Just as a reminder, if two polygons are considered congruent polygons, it means that they are exactly the same as one another. In other words, all the angles are congruent and all the sides are congruent between the two polygons. It means they're exactly the same. Similar polygons are almost congruent, but not quite. And you'll see what I mean in just a second. The definition of similar polygons are two polygons so that all the corresponding angles are congruent. So you can see we have kind of part of the definition of congruent polygons happening here. Similar polygons have corresponding angles that are all congruent, but their sides are not necessarily congruent. They are in proportion. The way I think of it typically is if I'm looking at two polygons that are similar, like I have in this diagram right here, I have polygon MNOPQ is similar to this little squiggly here. It's like the congruence sign without the equals part of it, right? That means is similar to polygon FGHIJ. What that means to me is that this guy here is just a kind of a shrunken version of this. They just took this polygon and they shrunk it down to make this one. Or maybe they started with this polygon and they just enlarged it to make this polygon. All right, so that's what it means to be similar in a way, if you want to kind of think about it in really kind of non-technical terms. Taking a figure and either shrinking it down or making it bigger, enlarging it. But based on the definition of similarity, what do we know if we know that these polygons are congruent? Are similar? Well, first of all, we know that there's angles that are congruent within these two polygons, right? We know that angle M right here is going to be congruent to one of the angles over here. But how do we know which one? We look right here at this statement. M will be matched up with corresponding to F. So I know that angle M is going to be congruent to angle F. And then I can kind of move around my polygons here, right? I know that angle N is going to be congruent to angle G. And I know that angle O will be congruent to angle H. I know that angle P will be congruent to angle I. And I know that angle Q will be congruent to angle J, right? All the corresponding angles will be congruent. And then I also know, part B of the definition, I know that the corresponding sides will be in proportion. So for instance, MN will not be equal to FG, because remember, this is a shrunken, this is a kind of a reduced version of this, a smaller version of this polygon right here. So MN will not be equal to FG, but if I take MN and I put it in a ratio with FG, that ratio will equal a few other ratios, right? It'll equal the ratio of NO to GH, and it'll equal the ratio of OP to HI, and it'll equal the ratio of PQ to IJ, and finally the ratio of QM to JF. All of these corresponding sides are in proportion. So if I match up a pair of corresponding sides as a ratio, I can set it equal to any other pair of corresponding sides in a ratio. If two polygons are similar, like these two right here, the ratio of the lengths of two corresponding sides is called the scale factor of the similarity. What is the scale factor of this one? So, well, if I take any one of these ratios, and remember, they're all equal, so it doesn't matter which one I pick. If I take any of these ratios, simplify it if possible, the result is my scale factor between the two similar figures. So, well, which one should I do? Should I do MN over FG? Well, the problem is there, I don't know what MN is, and I don't know what FG is. Should I do NO and GH? Don't know NO, don't know GH. Aha, here I have a ratio, OP and HI, where I can say that OP has a length of 10 and HI has a length of 4. So I can take this ratio right here. This is the one that works, right? This guy right here, it works because I have both of these lengths. So I can take that ratio, write it out with the numbers there, the lengths of those segments, and now reduce. I can divide that number by 2, and I can divide that number by 2, and I get 5 over 2. So 5 to 2, or 5 over 2, is the scale factor for this similarity right here. Let's look at another example. In this picture, we have A, B, C, D, similar to A prime, B prime, C prime, D prime. This is some kind of some labeling that you'll see a lot when dealing with similarity. They took all of these letters and they just tacked on this apostrophe to it. We call that A prime, B prime, C prime, and D prime. First of all, it wants us to find the scale factor of the bigger shape on top to the smaller shape. Now what we need to do is we need to look for a ratio that we can set up between two sides. Can I do AB over A prime B prime? No, because I'll have a Y over 12, right? Y over 12, that's not going to help me. I can't reduce that. I'm missing a number. Okay, but that should be the same as BC over B prime C prime. Well, that's 22 over Z. Again, don't have both numbers. Let's go around the shape. DC over D prime C prime. Aha! Look, there's one where I have two numbers, but just to finish this out, let's go ahead and make the last ratio 30 over x, right? 30 over x. But this guy right here, this is the one I want to concentrate on to make my ratio, my scale factor. I'm going to take 50 over 30. 50 over 30. I'm going to divide them both by 10. In other words, I'm just going to knock off a 0. And I got a 5 over 3 scale factor between these two. Well, now what's the values of x, y, and z? Well, here I have, where's my x? Here's my x, 30 over x. I know that 30 over x should reduce down to the scale factor, 5 over 3. Right? 30 over x should end up equaling 5 over 3. Well, now I have a proportion that I can solve, right? I can cross multiply. 30 times 3 equals 5 times x. So 90 equals 5x. And now 90 divided by 5, right? If I divide by 5 on both sides, 18 is my x. So there's x. X is 18. How about y? Well, y over 12 should also come down to 5 over 3. So if I cross multiply, I have 3y equals 5 times 12, which is 60. So that means y equals 20. Well, how about z? 22 over z should come down to my same scale factor, 5 over 3. Cross multiply, 22 times 3, that's 66, equals 5 times z. Well, this one's not going to come out as nice, is it? I got to divide by 5 on both sides. 66 divided by 5, that's going to be 13.2, I believe that comes out to. I might be wrong there, but I think it's 13.2. That's my value for z. So I got an 18 for my x, a 20 for my y, a 13.2 for my z, and I did that all using the scale factor. The scale factor is what every one of these ratios of corresponding sides should reduce down to. Right? They should all reduce down to the same thing, 5 over 3. Now it wants me to find the ratios of the perimeters. The ratio, really shouldn't be an S right there, the ratio of the perimeters. Well, what's the perimeter of the big shape? It's going to be 30 plus y, which is 20, plus 22, plus 50. What's that come out to be? 122. So my big shape has a perimeter of 122. My smaller shape here, let's see, it's x, which is 18, plus 12, plus z, which is 13.2, plus my 30. So what does this come out to? That's 30, and that's 30, that's 60, plus 13.2, that's 73.2. So now I want to make this ratio 122 over 73.2. Can I reduce that? Well, I got this weird decimal here, right? So what I'm actually going to do to try and reduce this is I'm going to actually go in the opposite direction. I am first going to multiply top and the bottom by 10. Why did I do that? Because it takes this decimal, 73.2, and it turns it into a non-decimal number, 732. So now I just need to check, does 1,220 over 732 reduce? And so I'm going to cheat a little bit here. I'm going to use my calculator, and I'm going to say, okay, I can divide, let's see, what can I divide both those numbers by? I can actually divide both those numbers by 244. Okay, I cheated a little bit there. It might take you a little longer to do this, but I'm just reducing a fraction here, right? Your calculator can do that really nice and easy for you. If I divide them both by 244, I get 5 over 3. Lo and behold, it's the same as the scale factor. So if I have two similar shapes that have a scale factor of 5 over 3, it looks like the ratio of their perimeters turns out to be the same as the scale factor, 5 over 3. Interesting. Just wanted to complete that, put that 73.2 there. All right, so there you have it. There's another example on your note sheet here. I'm going to leave that up to you. We'll probably discuss that one in class, but if you want to, please go ahead and try and do it. It's pretty much the same as the example that we just completed on the video.